Imagine, just for a moment, that you are floating in the void of space, not near Earth, not near the moon. You are 1.5 million kilometers away from home, 4 times farther than the moon, drifting at a point in space where the gravitational pull of the Earth and the Sun reach a delicate, silent equilibrium. There is no sound here, there is no air. There is nothing but the cold, endless black of the cosmos stretching out in every direction, farther than your mind can comprehend. And here, in this absolute silence, in this frozen emptiness, there is a machine, a golden machine, a machine with a mirror 6.5 meters wide, plated in a layer of gold, thinner than a human hair, folded like origami inside a rocket, and launched on Christmas Day in the year 2021. This machine has no crew. No human hands will ever touch it again. It simply sits here, rotating slowly in the darkness, pointing its enormous golden eye deeper and deeper into the abyss of the universe. And one day, it captured something. Something that made scientists around the world stop what they were doing. Something that generated thousands of research papers, ignited fierce debates in the most prestigious institutions on Earth, and forced humanity to confront a truth so profound, so unsettling, so fundamentally terrifying that it may change how we understand reality itself. This machine is the James Webb Space Telescope, and what it found is the subject of everything you are about to hear. Before we dive into the darkness, before we confront the image that shook the foundations of modern astrophysics, there is something you need to understand. You need to understand why this telescope exists, what makes it different from anything humanity has ever built, and why the things it sees carry a weight that no other instrument in human history has ever delivered. Because without that context, the images are just pretty pictures. With that context, they become doorways into the deepest truths the universe has to offer. The story of the James Webb Space Telescope begins not with its launch, but with its predecessor. In 1990, NASA launched the Hubble Space Telescope into low Earth orbit, approximately 547 kilometers above our planet. Hubble was a revolution. For the first time, humanity had an eye above the atmosphere, free from the blurring effects of Earth's air, capable of seeing the cosmos with a clarity that ground-based telescopes could only dream of. Hubble showed us things we had never seen before. It revealed that the universe was not static, but expanding, and expanding at an accelerating rate. It captured images of distant galaxies, exploding stars, and vast nebulae of gas and dust where new stars were being born. Hubble became humanity's most beloved scientific instrument, and its images became icons of human curiosity. But even as Hubble was delivering these revelations, scientists knew it had limits. Hubble sees primarily invisible light and a narrow range of ultraviolet and near-infrared wavelengths. This is a problem, because the oldest, most distant objects in the universe do not shine invisible light. Their light has been traveling through space for billions of years, and during that time, space itself has been expanding. This expansion stretches the wavelength of light, shifting it from the visible spectrum into the infrared. The oldest light in the universe, the light from the very first stars and galaxies, has been stretched so far that it is now invisible to Hubble. It exists only as infrared radiation, a form of light our eyes cannot see, and Hubble was not fully designed to detect. To see the birth of the universe, to witness the first light that ever shone in the cosmos, humanity needed a new kind of eye, an infrared eye, the most powerful infrared eye ever conceived. The idea for the James Webb Space Telescope was born in 1996, just 6 years after Hubble's launch. At that time, it was called the Next Generation Space Telescope. The concept was ambitious, but seemed achievable. NASA estimated the project would cost approximately $1 billion and could be ready for launch by 2007. That estimate turned out to be spectacularly wrong. The engineering challenges of building an infrared space telescope of the required sensitivity and size proved to be among the most difficult problems humans had ever attempted to solve. The primary mirror needed to be massive, far larger than Hubble's 2.4-meter mirror, to gather enough faint infrared light from the edge of the observable universe. The final design called for a 6.5-meter primary mirror composed of 18 individual hexagonal segments, each made of beryllium, an extremely lightweight and strong metal. Each segment was polished to a precision of approximately 10 nanometers, roughly 1/10,000th the width of a human hair, Then each segment was coated with a microscopically thin layer of gold, because gold is exceptionally efficient at reflecting infrared light, achieving over 98% reflectivity in the wavelengths Webb was designed to observe. But the mirror was only the beginning of the engineering challenges. An infrared telescope must be cold, extremely cold. If the telescope itself is warm, its own heat will radiate infrared light that would overwhelm the faint signals from distant galaxies. Webb's instruments need to operate at temperatures around -233 degrees Celsius, just 40 degrees above absolute zero. To achieve this, the telescope was designed with a sun shield, a structure the size of a tennis court composed of 5 layers of a material called kapton, each layer thinner than a human hair. The sun shield sits between the telescope and the sun, blocking solar radiation and allowing the telescope side to cool passively to the required temperatures. The sun-facing side of the sun shield reaches approximately 85 degrees Celsius, while the telescope side drops to -233 degrees Celsius. This temperature difference, more than 300 degrees across a gap of just a few meters, is maintained perpetually as long as the sun shield faces the sun. Here is the part that kept engineers awake at night for over 2 decades. The 6.5-meter mirror and the tennis court-sized sun shield were far too large to fit inside any existing rocket fairing in their deployed configurations. They had to be folded. The mirror was folded in 3 sections, like a drop-leaf table. The sun shield was folded into a compact bundle with hundreds of release mechanisms, pulleys, cables and motors that would unfurl it in space. The entire deployment sequence involved 344 individual mechanisms that all had to work perfectly. 344 single points of failure. If even one cable snagged, if one motor failed to fire, if one pin refused to release, the entire $10 billion mission would be compromised beyond repair. There would be no astronaut crew to fix it, no space shuttle to service it. Webb was heading to a location 1.5 million kilometers from Earth, far beyond the reach of any crewed spacecraft. Every mechanism had to work the first time, perfectly, in the vacuum of space. It is not an exaggeration to say that the deployment of the James Webb Space Telescope was one of the single most nerve-wracking engineering events in human history. On December 25, 2021, at 7:20 in the morning Eastern Time, an Ariane 5 rocket lifted off from the Guiana Space Center in Kourou, French Guiana, carrying the James Webb Space Telescope. The launch was nearly flawless, and in fact, the Ariane 5's precision was so extraordinary that it used less of Webb's onboard fuel than expected for course corrections, effectively extending the telescope's operational lifetime from a planned 10 years to potentially 20 years or more. Over the following 2 weeks, the sun shield unfurled, layer by layer. Then the mirror segments folded into position, each one individually adjustable by tiny actuators with a precision of 1/10,000th of a human hair. Every single one of the 344 mechanisms worked, every cable deployed, every pin released, every motor fired. It was, by any measure, a perfect deployment. Webb arrived at its destination, the second Lagrange point, known as L2, a gravitational equilibrium point, 1.5 million kilometers from Earth, on the side opposite the Sun. At L2, Webb orbits the Sun in lockstep with Earth, always keeping Earth and the Sun on the same side, always keeping its sun shield pointed at them, always keeping its instruments in the cold shadow behind the shield. It is the perfect location for an infrared observatory. And from that location, 1.5 million kilometers from home, the most powerful eye humanity has ever built opened for the first time and looked into the abyss. The first full-color scientific images from the James Webb Space Telescope were released on July 12, 2022. In an unusual move that underscored the significance of the moment, the very first image was unveiled not by NASA administrators in a press room, but by the President of the United States at the White House. That image was Webb's first deep field, a view of the galaxy cluster known as SMACS 0723. And it changed everything. To understand why this image shook the world, you first need to understand what you are looking at. The image shows a patch of sky so small that if you held a single grain of sand at arm's length against the night sky, it would cover approximately the same area. That is how tiny this slice of the cosmos is. And within that impossibly small patch of sky, JWST revealed thousands of galaxies, not stars, Galaxies. Each one of those galaxies contains hundreds of billions of stars. Each of those stars may have planets. The number of worlds contained in that single image, taken from a speck of sky the size of a grain of sand, is beyond what the human mind can meaningfully process. And this was taken with a combined exposure time of only 12.5 hours. When Hubble created its famous deep field images, it required weeks of accumulated exposure to achieve less detail over a similar area. Webb achieved its breathtaking depth in half a day. The galaxy cluster SMAC 0723, which dominates the center of the image, is located approximately 4.6 billion light-years away. That means the light we see from the cluster left those galaxies 4.6 billion years ago, before our Sun and Earth even existed. But the cluster itself is not what made this image terrifying. The cluster is acting as a cosmic magnifying glass, exploiting one of the most profound predictions of Albert Einstein's general theory of relativity. Einstein showed that mass warps the fabric of space-time, and light traveling through warped space follows that curvature. A sufficiently massive object, like a galaxy cluster containing trillions of solar masses of matter, bends the light from more distant objects behind it, focusing and magnifying that light like a giant lens. This phenomenon is called gravitational lensing, and SMAC 0723 is doing it spectacularly. The arcs, streaks, and distorted shapes you see scattered around the cluster in the image are not local galaxies. They are galaxies far, far behind the cluster. Galaxies whose light has been bent, stretched, and amplified as it passed through the warped space around SMAC 0723. Some of these gravitationally lensed galaxies are among the most distant objects ever observed, their light originating when the universe was less than 1 billion years old, barely 7% of its current age. Now consider the scale. That image covers an area of sky equivalent to a grain of sand at arm's length. The entire sky, as seen from Earth, is approximately 41,253 square degrees. Webb's first deep field covers a tiny fraction of 1 square degree. If you were to tile the entire sky with equally deep images, you would see not thousands but trillions of galaxies. Current estimates, informed in part by JWST data, suggest the observable universe contains approximately 2 trillion galaxies. Each of those galaxies contains, on average, hundreds of billions of stars. This puts the total number of stars in the observable universe at approximately 200 sextillion, that is a 2, followed by 23 zeros. And each of those stars may have planets. The total number of planets in the observable universe could easily be in the trillions of trillions. These are not guesses. These are conservative statistical extrapolations, based on actual observational data. And this is just the observable universe, the portion of the cosmos from which light has had time to reach us in the 13.8 billion years since the Big Bang. The actual universe, the totality of space that exists beyond our observable horizon, could be vastly larger, possibly infinitely larger. We will never know. Light from beyond the cosmic horizon has not had time to reach us, and because the universe is expanding at an accelerating rate, it never will. We are forever confined to our tiny bubble of observable reality, surrounded by an ocean of existence we can never see, never reach, and never comprehend. That is the first terrifying truth Webb revealed. Not a monster, not an alien, something far more unsettling, the sheer, incomprehensible scale of our cosmic insignificance. We are not just small, we are small beyond any capacity of the human brain to truly understand. And Webb showed us this in a single image, taken from a patch of sky so small you could cover it with a grain of sand. If you have ever looked up at the night sky and wondered what is really out there, what you are about to hear over the next hour and more is going to reshape your understanding completely. This is a journey from the spectacular to the disturbing, from the beautiful to the deeply unsettling. If you love space, if you love science, if you want to understand what the most powerful telescope ever built is revealing about the nature of reality, stay with us. Hit subscribe so you do not miss what comes next. Hit the like button because this story deserves to be heard. And leave us a comment telling us what you think is the most terrifying thing about the universe, because we are just getting started. Let us go deeper. Among the first 5 images released by JWST on that historic July day in 2022, one stood out for its raw, almost painterly beauty. It was an image of the Carina Nebula, specifically a region within it that scientists nicknamed the Cosmic Cliffs. The Carina Nebula is one of the largest and brightest nebulae in the southern sky, located approximately 7,600 light-years from Earth. A nebula is a vast cloud of gas and dust in interstellar space, and the Carina Nebula is enormous, spanning hundreds of light-years across. Within this grand structure, JWST focused on a specific region at the edge of a gaseous cavity within the nebula catalogued as NGC 3324. What it captured looks, at first glance, like a photograph of a mountain range at sunset, with craggy peaks bathed in golden light against a dark, star-speckled sky. The resemblance to a terrestrial landscape is uncanny and disorienting. But these are not mountains. These cliffs are walls of cold interstellar gas and dust, towering columns light-years in height. The tallest peaks in this image are approximately 7 light-years from base to summit. To put that in perspective, 1 light-year is approximately 9.46 trillion kilometers. These structures are tens of trillions of kilometers tall. They dwarf anything on any planet. They dwarf our entire solar system. And they are being sculpted, carved, and slowly destroyed by the very stars they helped create. The bright, glowing edge of the cosmic cliffs is being eroded by intense ultraviolet radiation and ferocious stellar winds from extremely hot, massive young stars located just above the top of the image frame. These stars, some of which are among the most luminous known, are blasting the gas cloud with so much energy that the surface layers are being stripped away, evaporated into space by the relentless bombardment of photons. This process, called photoevaporation, is gradually destroying the structure we see. In a few million years, these majestic cliffs will be gone, eaten away by the very stars they birthed. But here is where the image becomes something more than beautiful. Here is where it becomes profound, and yes, terrifying. Look behind the cliffs, look within the dust, because JWST, with its infrared vision, can see what Hubble never could. Infrared light passes through dust that blocks visible light, and when JWST peered through the opaque walls of the cosmic cliffs, it found what was hidden inside. Stars, hundreds of them, baby stars, protostars, in various stages of formation, embedded within the dust and gas, invisible to any telescope that could only see invisible light. Some of these protostars are launching jets of superheated gas at supersonic speeds, narrow beams of material firing outward from the poles of the forming star and slamming into the surrounding nebula. These are the tantrums of infant stars, announcing their existence with violence and fury. What looks like a serene, beautiful landscape is, in reality, a cosmic war zone. Stars are being born in explosions of heat and light. The gas cloud is being torn apart. Matter is being compressed, heated, ionized, and hurled through space at hundreds of kilometers per second. Creation in the cosmos is not gentle. It is ferocious. It is violent. And it is happening right now in structures so large that light itself takes years to cross them. JWST has captured some of the most stunning images of these stellar tantrums, these protostellar jets, in objects known as Herbig-Haro objects. Herbig-Haro objects are luminous regions formed when jets of gas ejected by newborn protostars collide with surrounding interstellar gas at incredible speeds. One particularly spectacular example is HH211, a bipolar jet from a very young protostar less than a few tens of thousands of years old, located in the Perseus molecular cloud. When JWST observed HH211, it revealed the jet in extraordinary detail, intricate shock waves, bright knots of compressed gas, and bow shocks where the jet material is ploughing into the surrounding medium. These features tell scientists about the physics of star formation, the mechanics of how newborn stars interact with their environments, and the conditions under which planets will eventually form in the disks of material orbiting these infant stars. Another striking observation was HH30, an edge on protoplanetary disks surrounded by bipolar jets, where JWST showed the disk structure with unprecedented clarity, revealing how the raw material for future planets is distributed around a star that is still in the process of igniting its nuclear furnace. These are not abstract theoretical objects. These are real places, real processes, happening right now in our own galaxy. And every single one of them is a reminder that the universe builds through destruction, creates through violence, and births new worlds from the ruins of old ones. Now, let us talk about one of the most iconic images in the entire history of astronomy, and what JWST did to transform our understanding of it. The Pillars of Creation. In 1995, the Hubble Space Telescope captured an image that became one of the most recognized photographs ever taken by a scientific instrument. It showed 3 towering columns of interstellar gas and dust within the Eagle Nebula, also known as Messier 16, located approximately 6,500 light-years from Earth in the constellation Serpens. These columns, immediately nicknamed the Pillars of Creation, became symbols of the beauty and grandeur of the cosmos. They are regions of active star formation, dense columns of cold molecular hydrogen gas and dust that are being eroded by the ultraviolet radiation from nearby hot stars, but within which new stars are being born. The tallest pillar stretches approximately 4 to 5 light-years from base to tip. When JWST turned its gaze upon the Pillars of Creation in October 2022, it captured them in 2 entirely different ways, using 2 different instruments, and each image told a profoundly different story. The first image, taken with the NIRCam instrument in near-infrared light, transformed the pillars. The dense, opaque dust columns that appeared dark and impenetrable in Hubble's visible light image became semi-transparent, almost ghostly. Through and within the dust, JWST revealed previously hidden protostars, glowing as bright red points of light. Some of these newly forming stars are still embedded deep within the columns, accumulating mass from the surrounding gas, growing toward the moment when nuclear fusion will ignite in their cores, and they will become true stars. The pillars themselves are studded with these infant stars, and many of them are launching jets of material that can be traced for light years. The NIRCam image showed the Pillars of Creation not as static monuments, but as dynamic, evolving structures, factories of stellar birth, teeming with activity invisible to any telescope that cannot see in infrared. The second image, taken with the MIRI instrument in mid-infrared light, revealed something entirely different and far more haunting. In mid-infrared, the stars nearly vanish. The brilliant points of light that dominate the NIRCam image fade to dim specks or disappear entirely, because at these longer wavelengths, the dust itself becomes the dominant emitter of light. The pillars, instead of appearing as semi-transparent structures filled with stars, transform into dark, opaque, sinister shapes against a faintly glowing background. They look like enormous, shadowy fingers reaching out of the void. There are no colors of starlight. There is no sense of creation or beauty. There is only cold dust, radiating its feeble glow into the emptiness. Many people who saw this MIRI image described it as eerie, unsettling, even terrifying. It strips away the beauty and reveals the raw, cold materiality of these structures. They are not monuments. They are not pillars. They are temporary accumulations of matter, briefly shaped by forces vastly beyond their control, destined to be destroyed by the very stars they are creating. And there is a truth about the Pillars of Creation that makes the image even more haunting. In 2007, observations from the Spitzer Space Telescope, an earlier infrared observatory, revealed evidence suggesting that a supernova explosion may have occurred near the pillars approximately 6,000 years ago. The shockwave from that explosion may have already reached and destroyed the pillars, but because the Pillars of Creation are 6,500 light-years away, the light showing their destruction has not reached us yet. What we see when we look at the Pillars of Creation, even through JWST's magnificent eyes, may be a ghost, a cosmic afterimage, a monument that no longer exists, shining in a sky that has already moved on. We are looking at the past, at something that may have been annihilated thousands of years ago, and we will not know for another 500 years or so. The light of its destruction is still traveling toward us through the void. Let us move deeper. Let us look at death itself through the eyes of JWST. In March 2023, NASA released a JWST image that captured a star in the act of dying. Not a quiet death, not a gentle fading, but a violent convulsive expulsion of its own body into space. The star is designated WR124, a Wolf-Rayet star located approximately 15,000 light-years from Earth in the constellation Sagittarius. Wolf-Rayet stars are among the rarest and most extreme stars in the known universe. They are massive, typically more than 25 times the mass of our Sun. They are intensely hot, with surface temperatures exceeding 45,000 degrees Celsius, more than 7 times hotter than our Sun's surface. And they are in their final evolutionary stages, burning through the last of their nuclear fuel at a prodigious rate, approaching the inevitable catastrophic end that awaits all massive stars, a supernova explosion. Before that final explosion, Wolf-Rayet stars go through a phase of intense mass loss. They shed enormous amounts of their outer material into space through powerful stellar winds that can reach speeds of thousands of kilometers per second. 124 has already shed material equivalent to approximately 10 times the mass of our Sun, expelling it into the surrounding space to form a glowing nebula of gas and dust, known as MOAN. 6-7. When JWST imaged WR-124, it revealed this nebula in detail that no previous telescope had achieved. The image is haunting. At the center sits the star itself, a blazing white point of concentrated fury. Surrounding it is a vast irregular halo of ejected material, glowing in shades of yellow, pink, purple, and orange in JWST's infrared view. The structure is chaotic and complex, filled with knots, clumps, and filaments of dust and gas. This is not a peaceful nebula. This is the wreckage of a star tearing itself apart, layer by layer, in preparation for its final, catastrophic detonation. The dust visible in this image is not just debris. It is cosmically significant material. Within those clumps and filaments are heavy elements that the star forged in its nuclear furnace over millions of years: carbon, silicon, oxygen, iron. When WR-124 eventually goes supernova, some of this dust will survive the explosion and be dispersed into the interstellar medium, seeding the surrounding space with the building blocks for future generations of stars and planets. The carbon in your body, the iron in your blood, the calcium in your bones were all forged inside stars like WR-124 and dispersed through exactly this kind of process. You are, quite literally, looking at a factory that is manufacturing the ingredients for future worlds and future life, and that factory is about to explode. We do not know exactly when WR-124 will go supernova. It could be in 10,000 years. It could be in 100,000 years. On a cosmic timescale, it is imminent. When it does, the explosion will, for a brief period, outshine its entire galaxy. The energy released will be staggering, equivalent to the total energy output of our Sun over its entire 10 billion year lifetime, compressed into a few weeks. The shock wave will propagate through space for thousands of years, sweeping up interstellar gas and triggering the formation of new stars. Death in the cosmos is not an ending. It is a transformation, a violent, terrifying, magnificent transformation. Not far from Wolf-Rayet 124 in the JWST image catalogue, but vastly different in nature, is another portrait of stellar death. The Southern Ring Nebula, also known as NGC 3132, located approximately 2,500 light-years away in the constellation Vela. This is what astronomers call a planetary nebula, a name that is misleading because it has nothing to do with planets. A planetary nebula is created when a star similar in mass to our Sun reaches the end of its life, exhausts its nuclear fuel, and sheds its outer layers into space. What remains is a tiny, incredibly dense remnant called a white dwarf, the collapsed core of the original star, no larger than Earth, but containing a significant fraction of the star's original mass. The expelled outer layers form an expanding shell of gas and dust that glows as it is illuminated by the intense ultraviolet radiation from the central white dwarf. When Hubble observed the Southern Ring Nebula, it captured a beautiful but somewhat simple image of concentric shells of glowing gas, surrounding what appeared to be a single star. When JWST observed the same object, it revealed a far more complex and dramatic reality. JWST's NIR CAM image showed 2 stars at the center of the nebula, not one. The brighter star as a companion, still alive and burning. The dimmer star, partially obscured by dust, is the dying white dwarf responsible for creating the nebula. This was the first time the white dwarf had been clearly resolved in such detail. But JWST went further. It revealed that the nebula's structure is far more intricate than previously known. Multiple shells of ejected material, each representing a different episode of mass loss from the dying star, are nested within each other like the layers of an onion. The pattern of these shells suggests that the dying star did not shed its material smoothly and continuously. Instead, it went through periodic, episodic outbursts of mass loss, each one expelling a new layer of material into space. Even more remarkably, analysis of the nebula's complex geometry suggested that the system may not be a simple binary pair, but could involve as many as 4 or 5 stars, whose gravitational interactions helped shape the nebula into its observed structure. The MIRI image revealed the molecular structure of the dust within the nebula, showing distributions of complex organic molecules, silicates, and other compounds spread through the expanding shells. This is the chemical legacy of a dead star, a dispersal of processed material back into the interstellar medium. And here is the truth that makes this image personal. Our Sun is a medium mass star. In approximately 5 billion years, it will exhaust the hydrogen fuel in its core, swell into a red giant star large enough to potentially engulf Mercury, Venus, and possibly Earth, and then shed its outer layers to form a planetary nebula, leaving behind a slowly cooling white dwarf. The Southern Ring Nebula is not just a beautiful image of a distant object. It is a preview of our Sun's future. It is a portrait of how our solar system will end, not in a supernova, not in a dramatic explosion, but in a slow, quiet expansion, a shedding of layers, and a long, cold fade into darkness. When you look at this image, you are looking at the future of your home star, and by extension, the ultimate fate of every world that orbits it. Let us shift our gaze now from the death of individual stars to something far more violent, far more dramatic, and far more vast. Let us look at galaxies colliding. Stephan's quintet is a visual grouping of 5 galaxies located in the constellation Pegasus, and it holds the distinction of being the first compact galaxy group ever discovered, identified by the French astronomer Édouard Stephan in 1877. 4 of the 5 galaxies, NGC 7317, NGC 7318A, NGC 7318b, and NGC 7319, are physically associated with each other at a distance of approximately 290 million light-years from Earth. They are locked in a complex gravitational interaction, slowly merging and tearing each other apart over hundreds of millions of years. The 5th galaxy, NGC 7320, is actually a foreground object, at only about 40 million light-years, coincidentally projected against the other 4. When JWST observed Stephan's quintet, it produced one of its largest images, a mosaic assembled from approximately 1,000 separate image files, covering an area of sky roughly 1/5 the angular diameter of the Moon as seen from Earth. The level of detail in this image is staggering. JWST revealed features never before seen in Stephan's quintet. It showed sparkling clusters containing millions of young stars, born from gas compressed by the gravitational interactions between the galaxies. It revealed long, sweeping tidal tails of gas and dust being ripped from the galaxies and flung into intergalactic space by gravitational forces, and it captured the enormous shockwave generated by galaxy NGC 7318 billion as it plunges through the center of the group at approximately 800 kilometers per second. This shockwave, stretching across tens of thousands of light-years, is heating gas to millions of degrees and triggering bursts of new star formation even as it destroys existing structures. Observations from ALMA, the Atacama Large Millimeter Array, combined with JWST data, have shown that this galactic shock is shaping the group in ways that are still not fully understood, influencing star formation rates and gas dynamics in mysterious and complex patterns. Perhaps the most significant feature JWST revealed in Stephan's quintet is the active galactic nucleus of NGC 7319. At the heart of this galaxy sits a supermassive black hole, approximately 24 million times the mass of our Sun, and it is actively feeding, consuming gas and dust that spiral into it, heated to extreme temperatures and emitting powerful radiation across the electromagnetic spectrum. JWST's spectroscopic observations revealed the detailed composition of the gas surrounding this supermassive black hole. Hot hydrogen, iron-rich gas, and silicate dust swirling in a gravitational maelstrom that would annihilate anything that ventured too close. This is what galaxies do when they meet. They do not peacefully coexist. They tear each other apart, steal each other's stars, compress each other's gas into new stellar nurseries, and feed their central black holes with the debris. It is creation and destruction on a scale that makes individual stellar deaths look like campfire sparks against a forest fire. And it is happening everywhere in the universe. Our own galaxy, the Milky Way, is on a collision course with the Andromeda Galaxy. In approximately 4.5 billion years, the two galaxies will begin to merge in a process that will take hundreds of millions of years and will completely restructure both galaxies. What JWST shows us in Stefan's quintet is a preview of our own galaxy's distant future. Now, let us turn to something that, when it was announced, sent a genuine shockwave through the scientific community and made headlines around the world for a reason very different from cosmic destruction. Let us talk about what JWST found in the air of worlds orbiting other stars. Before JWST, our ability to study the atmospheres of exoplanets, planets orbiting stars other than our Sun, was extremely limited. We knew some exoplanets existed. We knew their approximate sizes and masses, but their atmospheres were largely a mystery. JWST changed that completely. One of the telescope's most remarkable capabilities is its ability to perform transit spectroscopy. When a planet passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere on its way to us. Different molecules in the atmosphere absorb specific wavelengths of that light, leaving a unique chemical fingerprint in the spectrum. By comparing the spectrum of the star when the planet is in front of it to the spectrum when the planet is not, astronomers can identify which molecules are present in the planet's atmosphere. It is, in essence, tasting the air of a world hundreds of light years away. The first exoplanet whose atmosphere JWST analyzed in comprehensive detail was WASP-39b, a hot Saturn, a gas giant approximately the mass of Saturn but orbiting extremely close to its host star, completing one orbit every 4 Earth days. WASP-39b is located approximately 700 light-years from Earth, and its atmosphere is superheated by its proximity to its star. JWST's observations of WASP-39b were groundbreaking. The telescope detected, for the first time in any exoplanet atmosphere, carbon dioxide. This was a historic first, a molecule that had never before been directly identified in the atmosphere of a world beyond our solar system. But JWST did not stop there. It also detected water vapor, sodium-potassium, and evidence of photochemistry, specifically sulfur dioxide, a molecule produced by chemical reactions driven by the ultraviolet light from the host star interacting with molecules in the planet's upper atmosphere. This was the first time photochemistry had been detected on any exoplanet. WASP-39b itself is far too hot and gaseous to support life as we know it. But the detection of these molecules, and especially the evidence of active atmospheric chemistry, demonstrated that JWST can do something that was previously impossible. It can analyze the atmospheric chemistry of distant worlds with a precision and detail that opens the door to searching for biosignatures, chemical signs of life, on potentially habitable planets. And this brings us to K2-18b, the exoplanet that generated perhaps the most profound and controversial headlines of JWST's mission to date. K2-18b is a sub-Neptune exoplanet, approximately 8.6 times the mass of Earth, orbiting within the habitable zone of a red dwarf star approximately 120 light-years from Earth. The habitable zone is the range of distances from a star where conditions could potentially allow liquid water to exist on a planet's surface. K2-18b is not a rocky planet like Earth. It is larger and likely has a thick, hydrogen-rich atmosphere overlying what could be a global water ocean. This type of world is called a Hycean planet, a theoretical class of exoplanet with a hydrogen atmosphere and a liquid water ocean. When JWST analyzed K2-18b's atmosphere, it detected methane and carbon dioxide, both expected in a hydrogen-rich atmosphere. It also noted a deficiency of ammonia, which is significant because ammonia should be abundant in such an atmosphere unless it is being dissolved into a liquid water ocean. The chemical profile was consistent with a world that has a water ocean beneath a hydrogen atmosphere. But then came the detection that made headlines around the world. JWST found a possible, tentative signal of dimethyl sulfide in K2, 18B's atmosphere. Dimethyl sulfide, commonly abbreviated as DMS, is a molecule that on Earth is produced only by living organisms. It is primarily generated by marine phytoplankton, the microscopic algae that form the base of the ocean food chain. There is no known geological or atmospheric process that produces significant quantities of DMS. On Earth, it is an unambiguous biosignature, a chemical sign of life. The critical word here is possible. The detection was tentative, not confirmed. The signal was at the edge of the telescope's sensitivity, and the research team was careful to emphasize that additional observations are needed before any conclusions can be drawn. This is not a confirmed detection of life on another world. It is a possible hint, a tantalizing suggestion, an arrow pointing in a direction that, if confirmed, would represent the single most profound discovery in the history of science. Think about what that would mean. If dimethyl sulfide is confirmed in K2, 18B's atmosphere, it would strongly suggest that biological processes are occurring on a world 120 light-years from Earth. It would mean that life is not unique to Earth. It would mean that the universe is not just vast and violent and ancient, but alive. The implications for philosophy, for religion, for our understanding of our place in the cosmos would be staggering beyond calculation. And even if this specific detection is not confirmed, the fact that JWST can look for such signatures, that it has the sensitivity to detect the chemical fingerprints of biological activity on worlds orbiting other stars, means that the question, "Are we alone?" has moved from philosophy to observational science. JWST is not going to find microbes. It is not going to photograph alien life forms, but it may find the chemical calling cards of life in the atmospheres of distant worlds, and that is terrifying in the most profound sense of the word. If you are still with us, if this journey is expanding your understanding of what is out there, take a moment and hit that like button. Drop a comment below and tell us, do you think there is life beyond Earth? Do you think K2, 18B could harbour organisms in its alien ocean? If you are enjoying this exploration of the cosmos, subscribe to the channel because we are about to go even deeper to the edge of the observable universe, where JWST has found things that should not exist. Before JWST launched, the standard model of cosmology, known as lambda CDM, made specific predictions about what the early universe should look like. According to this model, the universe began with the Big Bang 13.8 billion years ago. In the first few 100 million years, matter slowly began to clump together under the influence of gravity, forming the first small, irregular protogalaxies. These early galaxies were predicted to be small, faint, chaotic, and messy, slowly growing over hundreds of millions of years through mergers with other small galaxies. The process was supposed to be gradual, hierarchical. Small structures formed first and slowly built into larger ones, the massive, well-structured galaxies we see in the nearby universe. Galaxies like the Milky Way with its beautiful spiral arms and hundreds of billions of stars were the end products of billions of years of this assembly process. They were not supposed to exist in the early universe. The early universe was supposed to be a place of small, dim, formless protogalaxies, gradually and painstakingly assembling into the grand structures we see today. JWST showed us something very different. When JWST began its deep surveys of the early universe, using programs like JDIS, the JWST Advanced Deep Extragalactic Survey, and others, it found galaxies existing in the first 300 to 500 million years after the Big Bang that were shockingly bright, surprisingly massive, and in some cases, remarkably well structured. These galaxies were not the small, faint, messy proto-galaxies that the models predicted. Some of them appeared to be as luminous as galaxies that should have taken billions of years to assemble. They were 100 times more abundant than theoretical models had predicted. The initial reaction in the astrophysics community was a mixture of excitement and alarm. Excitement because JWST was working even better than hoped, revealing the early universe in unprecedented detail. Alarm because what it was revealing did not match the predictions. Media headlines were dramatic. Impossible galaxies discovered. Crisis in cosmology. James Webb telescope breaks the universe. Scientists themselves use phrases like unexpectedly massive, luminous early galaxies. The concern was this: if these galaxies truly contained as many stars as initial estimates suggested, some appearing to rival the present-day Milky Way in stellar mass, then the standard model of cosmology was in serious trouble. There simply was not enough time in the first few 100 million years for that many stars to form through known physical processes. The star formation rates required would be physically impossible under the standard model. Something fundamental about our understanding of the universe would need to change. For a brief, exhilarating and terrifying period, it seemed like JWST might have broken cosmology. But science is a self-correcting process, and as follow-up observations and more careful analyses were conducted, the picture became clearer, though not necessarily less interesting. Several factors were discovered that had inflated the initial mass estimates of these early galaxies. One of the most significant was the presence of active galactic nuclei, actively accreting supermassive black holes at the centers of some of these galaxies. The light from these black holes, produced as matter spirals into them and is heated to extreme temperatures, was being mistaken for starlight from billions of stars. When the black hole contribution was properly accounted for, the galaxies appeared significantly less massive. Additionally, some of the photometric redshift estimates, the initial distance estimates based on the colors of the galaxies, were revised when spectroscopic confirmation became available. Some galaxies that appeared to be at extreme distances turned out to be somewhat closer and less luminous than initially thought. NASA's own analysis, led by Stephen Finkelstein and colleagues, concluded with a statement that was both reassuring and cautious. There is no crisis in terms of the standard model of cosmology. Any time you have a theory that has been well tested, the right response to surprising observations is to explore the observations more carefully before declaring the theory to be wrong. However, even after these corrections, the fact remains that galaxy formation in the early universe was significantly more efficient than anyone expected. The galaxies are not impossible, but they are surprising. Our models of how quickly stars can form in the early universe need to be refined. The mechanisms that drove such rapid assembly of stellar mass in the first few 100 million years are not yet fully understood. The standard model is not broken, but it is being stretched, tested, and forced to evolve in ways that no one anticipated before JWST opened its golden eye. Among the most remarkable galaxies JWST has discovered in the early universe is JDS-GS Zone 4, 0, which currently holds the record as the most distant galaxy ever spectroscopically confirmed. Its redshift is approximately 14.32, meaning the light we observe left this galaxy when the universe was only approximately 290 million years old, just 290 million years after the Big Bang, in a universe that is now 13.8 billion years old. This galaxy was already shining brightly enough for JWST to detect it across the entire observable universe. Its light has been traveling toward us for over 13.5 billion years. When that light began its journey, the universe was still in its infancy, still emerging from the cosmic dark ages, still in the process of forming its very first stars and galaxies. And yet, JD's GS Zone 4, 0 is not a dim, barely detectable smudge. It is genuinely luminous, and its light comes primarily from stars, not from a central black hole. This galaxy had already assembled a significant population of stars at a time when, according to our models, star formation should have barely been getting started. Even more intriguingly, spectroscopic analysis of JDS-GS Zone 4, 0 revealed an unusual enrichment of nitrogen, an element that typically requires multiple generations of stars to accumulate in significant quantities. In the local universe, nitrogen is produced primarily through the CNO cycle in intermediate mass stars, a process that takes hundreds of millions to billions of years to significantly enrich the interstellar medium. Yet here it is, abundantly present in a galaxy that existed when the universe was barely a few 100 million years old. One theory that researchers have proposed is that the dense environments of the early universe may have given rise to supermassive stars, stars vastly more massive than any observed in the modern universe, capable of producing unusually large amounts of nitrogen through processes that differ from those seen in present-day stellar populations. These supermassive stars may have lived fast, died young, and enriched their surroundings with heavy elements far more efficiently than any stars we know today. JDS-GS Zone 4, 0 also shows signs of actively clearing the primordial hydrogen fog surrounding it. contributing to the process astronomers call reionization. In the early universe, after the formation of neutral hydrogen atoms about 380,000 years after the Big Bang, the cosmos was filled with an opaque fog of neutral hydrogen gas. No light could travel freely through this fog. Then, as the first stars and galaxies formed and began emitting intense ultraviolet radiation, they started ionizing the surrounding hydrogen, breaking the neutral atoms back into their constituent protons and electrons, creating expanding bubbles of transparent, ionized gas through which light could travel. Over hundreds of millions of years, these bubbles grew and merged until the entire intergalactic medium was reionized and the universe became transparent. JD's GS Zone 4. Zero appears to be in the process of carving its own bubble, actively participating in this cosmic phase transition from darkness to light. Follow-up observations by ALMA, the Atacama Large Millimeter Array, detected oxygen emission from Jade's GS Zone 4, 0, meaning that not only had stars already formed and enriched the surrounding gas with heavy elements, but the conditions were complex enough for multiple elements to be detectable across billions of light-years of space and time. And then there is month over month, Z14, an even more distant galaxy confirmed at a redshift of 14.44, corresponding to a time when the universe was only approximately 280 million years old. Month over month, Z14 is one of the most luminous galaxies ever found at such an extreme distance, and it shows similar patterns of nitrogen enrichment found in the oldest, most ancient stars in our own Milky Way. This is a profound connection. The same chemical signatures found in the earliest galaxies at the edge of the observable universe are also found in the oldest surviving stars in our own galactic backyard. The fossils match the living history. Rohan Naidu of MIT, lead author of the study on month-over-month Z14, summarized the situation with a statement that captures the simultaneously thrilling and unsettling nature of these discoveries. With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted, which is both challenging and exciting. His colleague Jacob Shen added, "There is a growing chasm between theory and observation related to the early universe, which presents compelling questions to be explored going forward. A growing chasm between what we expected and what is actually out there. That chasm is one of the most terrifying and exciting frontiers in all of science." Now, let us talk about what might be the single most mysterious discovery JWST has made. Something so unexpected, so puzzling, that 4 years after its discovery, the astrophysics community is still debating what it even is. Let us talk about the little red dots. In JWST's very first data releases in 2022, as astronomers began examining the deep field images in detail, they started noticing something strange. Scattered across every deep field pointing of JWST's NIR camera, appearing in image after image, were small, compact, red-tinted objects that nobody had predicted and nobody could immediately explain. By the summer of 2023, multiple research teams had independently identified these objects and begun characterizing their properties. 3 common traits emerged. First, they were remarkably compact, appearing as nearly unresolved point sources even in JWST's exquisitely sharp images. Second, they had unusual V-shaped spectra, meaning their brightness as a function of wavelength formed a distinctive V pattern, being faint at short wavelengths, reaching a minimum, then rising steeply toward longer, redder wavelengths. Third, they showed emission lines from hydrogen gas moving at extremely high velocities, thousands of kilometers per second. These objects were found at significant cosmological distances, existing within the first billion years of cosmic time. They were not rare. A few appeared in every single deep field image JWST took. They accounted for a few % of all known galaxies in that epoch of the universe. And nobody knew what they were. They were dubbed little red dots, a deliberately informal name reflecting the uncertainty about their nature. The name stuck, and it has become one of the most discussed terms in modern astrophysics. 2 initial hypotheses were proposed, and both were extraordinary. The first hypothesis was that the little red dots were incredibly massive galaxies, containing enormous numbers of stars that had all assembled in less than a billion years. In this scenario, the V-shaped spectrum was explained by the combined light of a massive stellar population reddened by dust, The vertex of the V-shape resembled a feature called the Balmer break, produced by the absorption of light by hydrogen atoms in stellar atmospheres. The steep rise towards red wavelengths beyond the break would then be due to dust reddening, with the shorter wavelength light being starlight scattered out of the dust. However, the masses implied by this scenario were extraordinarily high, requiring star formation rates that seemed physically impossible given the short time available and the expected properties of dark matter halos at that epoch. The second hypothesis was that the little red dots were powered by supermassive black holes, actively accreting matter and shining through a cocoon of dust. The high-velocity hydrogen emission lines supported this idea, as they resembled the broad emission lines seen in active galactic nuclei, produced by gas clouds orbiting close to a supermassive black hole at tremendous speeds. However, the black hole masses implied by applying standard local calibrations to the observed gas velocities were staggering, ranging from 10 million to a billion solar masses. This would mean the black holes were comparable in mass to, or even more massive than, their host galaxies, a ratio roughly 1,000 times higher than the typical black hole-to-galaxy mass ratio observed in the local universe. These overly massive black holes would be extremely difficult to grow so quickly and would overproduce the total amount of black hole mass expected at that epoch. Both explanations required the objects to be heavily obscured by dust to explain their red colors. And this is where things got really interesting and really confusing. In 2024, multiple observational campaigns delivered a critical blow to both initial hypotheses. If dust was absorbing the ultraviolet and visible light from these objects and reddening them, then the conservation of energy demands that all that absorbed energy must be re-emitted by the dust at far infrared wavelengths. The dust should glow, telescopes sensitive to far infrared light should detect this glow. But when astronomers looked for it, in study after study, for individual luminous sources and for statistical samples, they found nothing. The far infrared emission that heated dust should produce was simply not there. The dust upper limits were stringent enough to conclusively rule out the entire class of models that relied on dust obscuration to explain the red colors. The little red dots are red, but not because of dust. Something else is making them red. At the same time, extended campaigns to observe the broader population of little red dots uncovered an even more remarkable subclass of objects, with extreme Balmer breaks so deep and so pronounced that they could not be produced by any known stellar population. The absorption by hydrogen atoms in the second energy level was clearly a key physical feature of these objects, but it was not happening in the atmospheres of normal stars. Whatever is producing the optical light in the little red dots, it is not starlight as we understand it. These twin discoveries eliminated the simple galaxy and simple black hole with dust explanations and opened a new, more complex and more mysterious chapter. The current leading hypothesis, as of 2026, is that the little red dots are powered by black holes accreting matter at very high rates, surrounded by dense, quasi-spherical envelopes of hydrogen gas. In this model, the dense gas, not dust, produces the observed red color through a combination of hydrogen absorption and the geometry of the gas distribution around the black hole. Because the black hole is more luminous per unit mass than initially assumed, due to the higher accretion rate, the inferred black hole masses can be much lower, perhaps around 1 million solar masses rather than 1 billion. This makes them far more natural occupants of the low-mass dark matter halos that were common in the early universe. But this picture is still incomplete and fiercely debated. Astronomers do not yet know the precise geometry of the gas envelopes. They do not know if the system is truly spherical or if viewing angle plays an important role. They do not know exactly how this dense gas accretes onto the black hole. There has been speculation that the little red dots may represent the end stages of black hole seed growth, a critical missing link in our understanding of how the first supermassive black holes formed. If this is true, then little red dots are not just mysterious objects. They are fossils of a process that shaped the entire subsequent history of the universe, the formation of the black holes that now sit at the centers of virtually every large galaxy, including our own. The CERN Courier, in a comprehensive review published in early 2026, concluded with a line that perfectly captures the state of the field. One thing we do know for sure, the more we learn about the little red dots, the more complex and unexpected they become. New papers attempting to explain them appear almost daily. the mystery is not being solved, it is deepening. And that, in the truest sense, is terrifying. Not because it poses any physical danger, but because it reveals the limits of our understanding. The universe contains phenomena that we cannot yet explain, phenomena that defy the categories we have built over decades of research, phenomena that may require entirely new physics to comprehend. The little red dots lead us naturally to one of the deepest puzzles in modern astrophysics, the origin of supermassive black holes in the early universe. Before JWST, the earliest known supermassive black holes existed when the universe was approximately 700 to 800 million years old. Even at that age, they were already monsters, containing billions of solar masses crammed into a region of space smaller than our solar system. The mystery of how these black holes grew so massive so quickly has haunted astrophysics for years. The problem is straightforward to state. A black hole grows by accreting matter, pulling in gas and dust from its surroundings. But there is a theoretical maximum rate at which a black hole can accrete matter, known as the Eddington limit. Beyond this rate, the radiation pressure from the infalling superheated material pushes incoming gas away, limiting how fast the black hole can grow. Even if a black hole started at a modest size and accreted at the maximum Eddington rate continuously for hundreds of millions of years, it would struggle to reach billions of solar masses by the time we observe these early monsters. Something does not add up. JWST has sharpened this puzzle considerably. It has found supermassive black holes at even earlier epochs than previously known. The galaxy GN Z11, one of the most distant galaxies known, seen as it appeared approximately 400 million years after the Big Bang, was confirmed by JWST to host a rapidly accreting supermassive black hole. Researchers at the University of Arizona discovered a cosmic shapeshifter, a galaxy observed just 800 million years after the Big Bang that appeared as a normal galaxy at some wavelengths, but revealed itself to be dominated by a supermassive black hole at others. These discoveries are pushing the black hole formation problem to earlier and earlier epochs. If massive black holes already existed just a few hundred million years after the Big Bang, they had even less time to grow than we previously thought, making the puzzle even harder to solve. Several theories have been proposed to explain how these primordial black holes formed. The first is the direct collapse hypothesis. In the early universe, under specific conditions, massive clouds of pristine hydrogen gas could have collapsed directly into black holes of 10,000 to 100,000 solar masses without first forming stars. These heavy seeds would have had a significant head start, requiring much less time to grow to supermassive proportions. The conditions required for direct collapse are very specific. The gas must be free of heavy elements that would cause it to cool and fragment into stars, and it must be bathed in intense ultraviolet radiation from nearby sources. But the early universe may have provided such conditions in certain regions. The second theory involves the remnants of the very first generation of stars, known as population 3 stars. These stars, which have never been directly observed, are predicted to have been extremely massive, potentially hundreds of times the mass of our Sun, because the primordial gas from which they formed, lacking heavy elements, could not cool efficiently and therefore collapsed into fewer but larger objects. When these massive population 3 stars exhausted their fuel and died, they would have left behind black hole remnants of perhaps 100 to 1,000 solar masses, which could then serve as seeds for future growth. A third, more speculative theory involves what some researchers have called black hole stars, massive gas clouds with black holes growing at their centers, which could appear as luminous, compact objects in the early universe, potentially resembling the little red dots JWST has discovered. JWST data has provided evidence supporting the direct collapse theory, backing theoretical predictions that have been made more than a decade ago, but which, until now, lacked observational support. The implications of these discoveries are profound. If supermassive black holes formed easily and early in the universe's history, then the role of black holes in shaping cosmic evolution may be far more significant than previously understood. It is possible that the first major structures in the universe were not galaxies of stars, but rather black holes, dark gravitational engines that began shaping the cosmos before the first stellar light had even finished clearing the primordial fog. The monsters may have come first, and everything else, the stars, the galaxies, the planets, the life, may have been shaped in their shadow. There is another deep mystery that JWST is addressing, one that strikes at the very foundations of our understanding of the universe. It is called the Hubble tension, and it is one of the most pressing unsolved problems in all of physics. The Hubble constant, designated H0, is a number that describes the rate at which the universe is currently expanding. It tells you how fast a distant galaxy is receding from us as a function of its distance. If H0 is, say, 70 kilometers per second per megaparsec, it means that for every megaparsec of distance, which is approximately 3.26 million light-years, a galaxy is receding from us at an additional 70 kilometers per second. The Hubble constant is one of the most fundamental numbers in cosmology. It determines the age, the size, and the ultimate fate of the universe. And we have a problem. We have two ways of measuring it, and they give two different answers. The first method uses the distance ladder. Astronomers measure the brightness of specific types of stars called Cepheid variables, which pulsate at rates directly related to their intrinsic luminosity, providing a reliable way to determine their distances. These Cepheid distances are then used to calibrate the distances to type Ia supernovae, a class of stellar explosions that all reach approximately the same peak brightness, making them visible across vast cosmic distances. Using this method, the Hubble Space Telescope, and now JWST, have determined H0 to be approximately 73 kilometers per second per megaparsec. The second method works backward from the cosmic microwave background, the faint radiation left over from the Big Bang, which was mapped with extraordinary precision by the European Space Agency's Planck satellite. By analyzing the detailed patterns in this ancient radiation, cosmologists can determine the physical conditions of the early universe and use the standard model of cosmology to calculate what the Hubble constant should be today. This method yields approximately 67.4 kilometers per second per megaparsec. These two numbers are close, but they are not the same. And the discrepancy is not within the margin of error. Both measurements have been refined to such precision that the probability of the disagreement being due to random statistical fluctuation is extremely low. The difference is real, and it has persisted for over a decade. When JWST began its observations, some scientists hoped it would resolve the tension by revealing that Hubble's Cepheid measurements were contaminated by systematic errors, perhaps because of crowded stellar fields where the light of Cepheids blended with other stars, skewing the distance estimates. In 2023, JWST cross-checked Hubble's Cepheid measurements with its superior resolution and confirmed that they were accurate. The Cepheid distances were not significantly biased. In December 2024, the largest JWST study of the universe's expansion rate, conducted by researchers at Johns Hopkins University, confirmed the Hubble tension is real and statistically significant. The discrepancy was not an artifact of measurement error. The universe genuinely appears to be expanding faster than the standard model of cosmology predicts. This means one of three things. Either there is some subtle, undiscovered, systematic error in one of the measurement methods that the entire global community of astronomers has failed to find over more than a decade, or the standard model of cosmology, lambda CDM, which has successfully described the large-scale structure and evolution of the universe for over 2 decades, is incomplete or incorrect in some fundamental way. Or there is new physics, some force or particle or process beyond our current understanding that is causing the universe to expand faster than expected. This could be an early form of dark energy, or dark energy that changes its strength over time, or an entirely unknown particle or interaction that we have not yet conceived of. This is not fringe speculation. This is one of the most active areas of research in theoretical and observational physics. The Hubble tension is a crack in the foundation of our understanding of the cosmos, and JWST is providing the data that will eventually either heal that crack or break it wide open. Either way, the answer will change physics. And the fact that we do not yet know the answer, that our best models of the universe may be fundamentally incomplete, is a kind of terrifying beauty. It means the universe is stranger than we have imagined. Closely related to the Hubble tension, and equally profound, is the question of dark matter. Approximately 27% of the total mass energy content of the universe is composed of dark matter. Dark matter does not emit light. It does not absorb light. It does not reflect light. It does not interact with the electromagnetic force at all, as far as we can tell. We cannot see it, touch it, or directly detect it with any existing instrument. We know it exists because of its gravitational effects. Galaxies rotate too fast for the amount of visible matter they contain. Stars at the edges of spiral galaxies orbit at velocities that can only be explained by the presence of a large amount of unseen mass. Galaxy clusters hold together despite not having enough visible mass to generate the required gravity. The large-scale structure of the universe, the cosmic web of filaments and voids that galaxies are distributed along, matches the predictions of models that include dark matter, but not models without it. JWST has contributed to the study of dark matter in a remarkable way. Using observations of approximately 800,000 galaxies, JWST enabled the creation of the most detailed map of dark matter ever produced. The technique is called weak gravitational lensing. When light from distant galaxies passes through regions of space that contain dark matter, the gravitational influence of the dark matter subtly distorts the shapes of those background galaxies. The distortion is far too slight to be noticed in any individual galaxy, but by statistically analyzing the shapes of hundreds of thousands of galaxies, astronomers can map the distribution of dark matter along the line of sight. The resulting map reveals the cosmic web in stunning detail. Dark matter forms an intricate network of filaments, like the strands of an impossibly vast spider's web, stretching across hundreds of millions of light years. At the densest nodes of this web sit galaxy clusters, the largest gravitationally bound structures in the universe. Between the filaments are voids, enormous regions of nearly empty space, some spanning hundreds of millions of light years across, where there is almost nothing. No galaxies, no stars, no planets, just the cold, dark emptiness of intergalactic space. This map has higher spatial resolution and extends to greater depths than any previous dark matter map, including those made with the Hubble Space Telescope. It shows how the invisible dark matter scaffolding overlaps and intertwines with the visible matter, the galaxies and clusters of galaxies that we can see. Visible matter traces the dark matter distribution, like cities built along the banks of an invisible river. Without dark matter, those galaxies would not exist. Without dark matter, the gravitational wells that attracted gas, enabled star formation, and built the cosmic structures we inhabit would not be there. We owe our existence to a substance we cannot see, cannot touch, and do not understand. And the most sobering part is this: everything we can see in the universe, every star, every galaxy, every nebula, every planet, every person, every atom of every element in the periodic table constitutes less than 5% of the total mass energy content of the universe. Approximately 27% is dark matter. Approximately 68% is dark energy, the mysterious force driving the accelerating expansion of the universe. We, and everything we know, are a tiny minority, a thin scattering of visible matter on the surface of a vast, dark ocean we cannot fathom. Now let us leave the large-scale cosmic web and the mysterious dark substances and return to something closer to home, something strange and unsettling in a very different way. Let us talk about rogue planets and the bizarre objects JWST found drifting through the Orion Nebula. In October 2023, JWST turned its infrared gaze upon the Orion Nebula, one of the closest and most studied star-forming regions in the Milky Way, located approximately 1,344 light-years from Earth. The Orion Nebula is a vast stellar nursery, a cloud of gas and dust within which new stars are actively being born. Astronomers expected to find protostars, jets, and the usual signatures of star formation that they had studied for decades. They found all of that. But they also found something nobody expected. Scattered throughout the nebula were 540 planetary mass objects. Objects with masses similar to Jupiter, ranging from about 1 to 13 Jupiter masses that were not orbiting any star. They were free-floating, drifting through the nebula unattached to any stellar system, alone in the interstellar medium. These are called rogue planets, and while their existence had been predicted, and a few candidates had been detected before, nobody expected to find 540 of them in a single nebula. But the truly bizarre discovery was what made this observation unique in the history of astronomy. Among those 540 planetary mass objects, 42 were found in pairs of Jupiter mass objects, gravitationally bound to each other, orbiting a common center of mass, floating freely through space, with no parent star. These paired rogue planets were given the name JUMBOs, Jupiter mass binary objects. Nothing like them had ever been observed before. Nothing in existing theories of planet formation or star formation predicted their existence. The mystery of the JUMBOs is this: how do you get two Jupiter mass objects bound together in the middle of interstellar space? There are two main theories for how individual rogue planets form. The first is that they form like stars from the gravitational collapse of small gas clouds, but simply do not accumulate enough mass to ignite nuclear fusion. In this view, they are essentially failed stars. The second theory is that they originally form around stars as normal planets, but are gravitationally ejected from their parent systems through interactions with other planets or passing stars. Both of these theories can explain individual rogue planets, but explaining binary pairs is much harder. If two planets were ejected from a star system, the ejection process is typically violent and chaotic, and it would be extraordinarily unlikely for two ejected planets to remain gravitationally bound to each other during the process. If they formed from collapsing gas clouds, the clouds would need to be remarkably small and would need to fragment in a very specific way to produce two Jupiter mass objects in a stable binary orbit. Simulations conducted in 2024 offered some possible pathways involving simultaneous ejection from star systems under very specific conditions. But the debate continues. Some researchers have even questioned whether the JUMBOs truly exist as physical pairs, or whether some could be chance alignments, though the statistical analysis strongly suggests that at least many of them are genuinely gravitationally bound. In a separate but related discovery, JWST's deepest survey of rogue worlds found 6 additional rogue planets in another region, including the lightest rogue planet ever identified. One of these rogue worlds was found to have a debris disk surrounding it, a disk of dust and small particles that, in a normal stellar system, would be the raw material from which moons or rings could form. A rogue planet with a debris disk is a strange and evocative concept. A world drifting through the interstellar void, utterly alone, no sun in its sky, no daylight, no warmth from a parent star, yet carrying with it a miniature system of orbiting material, a set of potential moons or rings that orbit in eternal darkness. Statistical models suggest that rogue planets may be extremely common. Some estimates indicate that there could be billions, possibly trillions of rogue planets in our galaxy alone, potentially outnumbering stars. Most of them are utterly invisible, detectable only by their faint infrared glow, residual heat from their formation slowly radiating away into the void, or through brief gravitational microlensing events when a rogue planet passes between us and a distant star. The thought that the space between the stars is populated by countless dark, unseen worlds drifting silently through the galaxy is both fascinating and deeply unsettling. And some of these rogue worlds, particularly the more massive ones, might maintain subsurface liquid water through internal heat sources, radioactive decay, or tidal heating in binary systems. Life, or at least the conditions for life, could potentially exist on worlds that have never known sunlight, drifting through the eternal night between the stars. While these rogue worlds wander the galaxy unattached, JWST has also been observing the opposite process, the construction of solar systems around newly born stars. Protoplanetary disks, flat disks of gas and dust surrounding young stars, are the cradles in which planets form. Our own solar system formed from such a disk approximately 4.6 billion years ago. Everything we are, every planet, every moon, every asteroid, every grain of sand on every beach, every molecule of water in every ocean, was once part of a protoplanetary disk surrounding our infant sun. JWST has captured images of these disks around other stars with unprecedented clarity and detail. It has observed disks edge on, revealing their vertical structure, their dark dust lanes, and the scattered light from their central stars. It has observed disks face on, revealing concentric rings and gaps that indicate where planets are actively forming, carving out clean orbits within the disk as they sweep up material, and grow. JWST has detected water vapor, silicates, and complex organic molecules within these disks, the chemical ingredients for habitable worlds present in the same types of structures that gave birth to Earth. We are watching, in real time on a cosmic scale, the same process that created our home world playing out around distant stars. Other Earths may be forming right now, assembling from the dust and gas of protoplanetary disks that JWST can see. To fully appreciate the terrifying depth of what JWST has revealed, we need to understand one of the most profound periods in the history of the universe, an epoch that was one of JWST's primary reasons for existing. It is called the Epoch of Reionization, and it is the story of how the universe went from utter darkness to light. After the Big Bang, for the first 380,000 years, the universe was a hot, dense, opaque plasma, a soup of protons, electrons, and photons so dense that light could not travel freely. Photons were constantly being absorbed and re-emitted, scattered in every direction. The universe was bright but opaque, like being inside a fog so thick you cannot see your hand in front of your face. Then, approximately 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms for the first time. A moment called recombination. With the free electrons now bound up in atoms, photons were finally free to travel through space unimpeded. This released the cosmic microwave background, the oldest light in the universe, which we can still detect today as a faint microwave glow filling all of space. But recombination, paradoxically, plunged the universe into darkness. Neutral hydrogen gas does not glow. There were no stars, no galaxies, no sources of light anywhere. The cosmic microwave background photons were redshifted to longer and longer wavelengths as space expanded, becoming invisible. The universe entered what astronomers call the cosmic dark ages, a period lasting hundreds of millions of years during which the cosmos was filled with nothing but vast clouds of cold, neutral hydrogen gas expanding through an utterly lightless void. No light, no structures, no complexity, just darkness, silence, and cold. Then, somewhere between 100 and 250 million years after the Big Bang, the first stars ignited. These were the population 3 stars, the very first generation of stars in the history of the universe. They formed from the primordial gas, composed almost entirely of hydrogen and helium, the only elements produced in the Big Bang. Because this pristine gas lacked the heavier elements that help gas cool and fragment in modern star-forming regions, the first generation of stars are predicted to have been vastly more massive than typical modern stars, perhaps hundreds of times the mass of our Sun. They burned with an intensity that defies imagination, their surfaces blazing at temperatures far hotter than any star we see today, and their intense ultraviolet radiation began to transform the universe. When ultraviolet photons from these first stars struck the surrounding neutral hydrogen gas, they had enough energy to ionize the hydrogen, stripping electrons from the atoms and converting the neutral gas back into a plasma of protons and electrons. This created expanding bubbles of ionized transparent gas around each of the first stars and galaxies. Within these bubbles, light could travel freely. Beyond the bubbles, the neutral hydrogen fog remained opaque. Over hundreds of millions of years, as more and more stars and galaxies formed, the ionized bubbles grew larger and began to overlap and merge. Eventually, by approximately 1 billion years after the Big Bang, the bubbles had merged completely, and the entire intergalactic medium was ionized and transparent. The cosmic dark ages were over. The universe had gone from dark to light. This transition is called reionization, and understanding its timeline, its drivers, and its mechanisms was one of the 4 primary science goals for which JWST was built. JWST's observations at extremely distant galaxies like JDS-GS Zone 4, 0 and month-over-month Z14 are directly probing this epoch. These galaxies show signs of actively ionizing the neutral hydrogen around them, carving their own bubbles of transparency in the primordial fog. JWST has confirmed that galaxies, not quasars, were the primary drivers of reionization, settling a long-standing debate, and the detection of heavy elements like oxygen in JDS-GS Zone 4. 0 by ALMA means that the first generations of stars had already lived, fused hydrogen and helium into heavier elements, and died, enriching the surrounding gas, all within the first few 100 million years of cosmic history. The universe wasted no time, even in its earliest chapters. Even when it was barely a few 100 million years old, it was already building, destroying, enriching, and transforming itself with a ferocity that our models had not predicted. There is something deeply moving about this. We are seeing the moment the universe woke up, the cosmic dawn, the first light that ever shone in a universe that had been dark since its birth. Those photons, the first photons from the first stars, have been traveling toward us for over 13.5 billion years. When JWST captures them, it is capturing the oldest accessible light in the universe. Light that left its source before galaxies as we know them existed, before the cosmic web had fully formed, before any of the structures that define our universe today had taken shape. It is light from a universe so young that it was still deciding what kind of place it was going to become. JWST has not only looked at the distant universe, it has also turned its infrared eye toward our own solar system, revealing familiar worlds in unfamiliar and striking ways. When JWST observed Jupiter, the largest planet in our solar system, it captured images in infrared that revealed features in visible light. Jupiter's massive auroras, electromagnetic storms at the planet's poles, driven by its incredibly powerful magnetic field and energized by volcanic material ejected from its moon Io, blazed brilliantly in JWST's infrared images. The Great Red Spot, a storm larger than Earth that has been raging for at least 350 years, appeared as a bright feature, and the planet's faint ring system, barely detectable in visible light, was clearly visible. The atmospheric banding that defines Jupiter's appearance was revealed in new detail, showing the complex layered structure of the planet's atmosphere, with different chemical compositions and temperatures at different altitudes. Saturn, too, was observed by JWST, and the result was striking and almost eerie. In certain infrared wavelengths, methane in Saturn's atmosphere absorbs almost all incoming light, making the planet itself appear extraordinarily dark, almost black. Meanwhile, Saturn's iconic rings, composed primarily of water ice, reflected infrared light brilliantly. The result was an image where the planet is a dark void encircled by bright glowing rings, a stark reversal of what we see in visible light, where Saturn is a luminous golden globe surrounded by pale rings. This image, while scientifically informative about the composition and temperature of Saturn's atmosphere and rings, is also visually disconcerting, a reminder that our familiar solar system looks completely different when seen in wavelengths our eyes cannot perceive. JWST has also contributed to the study of two of the most intriguing moons in our solar system, Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Both of these moons are believed to harbour vast subsurface oceans of liquid water beneath their icy shells. Europa's ocean may contain more water than all of Earth's oceans combined, kept liquid by tidal heating generated by Jupiter's immense gravitational pull. Enceladus is known to eject plumes of water vapour and ice particles from cracks in its south polar region, geysers that shoot material hundreds of kilometres into space. JWST's infrared observations have contributed to our understanding of the composition of material associated with these moons, adding to the growing body of evidence that the conditions necessary for life, liquid water, chemical energy, and organic molecules may exist in our own solar system, not just on distant exoplanets. Now, as we approach the end of this journey, let us try to put together the full picture of what JWST has revealed, and why the totality of it can only be described as terrifying.